Assalamu alaikum students. Today we are going to discuss some of the topics that we covered previously to have a short wrap up of the subject that we have already discussed, and we'll move forward to polarization mode dispersion. First of all, I would like to revise the Gaussian beam. That is the behavior of the light beam as a in terms of a Gaussian curve. Basically, it follows a Gaussian curve. What does that mean? Actually, experimental analysis has shown us that the light beam does not have strict boundaries. Rather, it has a Gaussian curve. That is, the central point of the beam has the highest intensity. While as we move away from the center point of the beam, the intensity reduces. So this plays a very important part in our study of dispersion in optical fiber communication. If you go to slide number 5 of the presentation that I've already sent to you, you will see a few descriptions about the Gaussian beam. It is observed that the light beam is most intense in the center, and then their intensity gradually decreases towards the outward direction. You can go to the slide number 6, in which there is a cross section shown in the figure. In the center point, the intensity is very high, but as we move away from the center point, intensity reduces. This can also be shown as a cross section at the center point. If we see the relative intensity, it is at the highest point, and we call it 1. As we move away from the center point, the intensity reduces. Here we are showing the physical distance, which is represented by R. As already said, that a light beam follows a Gaussian curve. Basically, it follows the Gaussian equation. Here in this equation, R is the distance of the point at which we are measuring the intensity, and I of R is the intensity at that particular point. I naught is the intensity at the 0 point or the central point. This is the intensity. This is we are showing the relative intensity, but actual intensity is given by I of 0 or I naught. Then we have got exponential of minus 2 R square over W naught square. R is the distance at which we are finding out the intensity, and W naught is the mode field diameter. Since the beam has no finite spread, So there is no natural measure of beam's intensity. So we define a parameter mode field diameter, which is 2 times W naught. If R is equal to W naught, then what would happen to this equation? These two terms would cancel out. R square, if it is equal to W naught square, then these two terms would cancel out, and we would be left with e raised to minus 2, which gives the value 0.135. So the mode field diameter is the cross-sectional dimension 2 times W naught, where the beam's intensity drops to 0.135 times the peak value. The data sheets that are provided by the manufacturers normally show the mode field diameters rather than the physical core diameter of a single mode fiber. In multimode fiber, all the light is confined inside the core. The reason being the fact that the core of a multimode fiber has a large radius. It has a large diameter. You know that its diameter is 62.5 micrometers as compared to 8 micrometers physical dia of a single mode fiber. So this does have a profound effect on the single mode fiber. Actually, what happens is that the mode field diameter that we come to find out, it is a little bit larger than the physical core diameter. The physical core diameter is, if it is 8.3 micrometers, and the mode field diameter is 9.3 micrometers. But this is just an example. So this does have some effect on the optical fiber communication in terms of dispersion. So let's see what type of dispersion it is adding upon. While in single mode fibers, some portion of light, approximately 20% of light, would be carried by the cladding. Now what happens if the light is carried by the cladding? Actually, when light goes through cladding, it undergoes a very relatively smaller refractive index. This smaller refractive index causes or brings about an easier path for the light, while so it has more velocity, while the velocity within the core is much less, right? Approximately 20% of the light is traveling through the cladding, while 80% goes through the core. There is a profound difference between the velocities of these two portions, and the light that goes through the core arrives at the destination a bit late as compared to the light that goes through the cladding. If you go to the slide number 9 of this lecture, you can see the first picture on the left side. It shows the index profile of the fiber, in which you can see clear boundaries of the core and the cladding. N1 is the refractive index of the core, which is higher, and N2 is the refractive index of the cladding, which is lower. Now, when actual beam of light travels through this optical fiber, 80% of this light travels through the core, because the shape of this light, the shape of the front of this light is somewhat Gaussian. I'm calling it Gaussian because the central point is has the highest highest intensity. As we move away from the central point, the intensity reduces until the point comes when this beam spreads beyond the diameter of the core, and it goes into the cladding. You can see this in this particular slide number 9, in which it is clearly shown that the mode field diameter of this particular beam, which is 2 times W naught, is greater than the physical diameter of the core of this optical fiber. So let's see what effect does it have on our communication. Typical values of mode field diameter are 9.3 micrometers, while the core diameter or the physical core diameter is 8.3 micrometers. Light beams propagate mostly in core and partially within the cladding. 80% of the light moves through the core and 20% through the cladding. The effective refractive index, or N effective, is the combination of core and cladding refractive indices in this particular case. Mode field diameter depends on operating wavelength also. The shorter the wavelength, lesser the mode field diameter. Now you can go to the slide number 11 of this file, and you can see a comparison of mode field diameters of 2 different types of fibers: the matched cladding fiber and the depressed cladding fiber. As already discussed, if we have a particular type of fiber in which the index profile of the fiber shows that there is a sharp depression in the refractive index of the cladding just after the core, then it would give a better result, because the mode field diameter would be smaller as compared to the matched cladding fiber. As we move from smaller wavelengths to the higher wavelengths, the mode field diameter increases. But both of these fibers show a persistent difference between each other, and but the mode field diameter increases continuously, almost linearly. You can see this in slide number 11 of the file that I have sent. Mode field diameter is considered in fiber splicing also. That is also a very important point where we need to know the mode field diameter of the fiber. Because if there is a mismatch of the mode field diameters on the 2 ends that we are going to join through fusion splicing, heat fusion splicing, then the attenuation would be much more. If the fibers have different mode field diameters, then there would be some extra insertion loss primarily. Now let's see what is the cutoff wavelength. It is the shortest wavelength at which a fiber can support single mode operation. As we increase the frequency or decrease the wavelength, single mode operation becomes more and more difficult. Two more things upon which single mode operation or the number of modes depend upon is the dia of the core and the refractive index, and also one more thing, that is the numerical aperture, which is under root n1 square minus n2 square. If the operating wavelength is chosen less than lambda c, which is the critical or the cutoff wavelength, then more than one mode will propagate along the fiber, which is not wanted in a single mode fiber. So same fiber can be a single mode or a multi-mode fiber depending upon the operating wavelength. Although in reality a fiber is made either single mode or multi-mode during the production phase, and as you know, the physical difference between the two is that the single mode fiber has a core diameter of 8.3 micrometers, while the core diameter of a multi-mode fiber is approximately 62.5 micrometers. But what happens is that if we use light that has a wavelength lesser than 1310 micrometers, then definitely it would lead us to additional modes, even if we are using a fiber with a core diameter of 8.3 micrometers. For single mode, the operating wavelength is always longer than lambda c. For single mode fiber, the operating wavelength is always longer than lambda c. As you know that the number of modes that we calculate in a fiber depends upon a particular value V, which is basically the V number, which is equal to pi d over lambda into under root n1 square minus n2 square, and the number of modes that travel in that particular fiber are V square over 2 in case of a step index fiber, while in a graded index fiber this value would be V square over 4. For a single mode operation, we need to have the V value to be 2.405. If we put this value 2.405 in place of V and try to find out the value of lambda in this particular equation, we can take lambda here and V here. we can replace this V with that particular value, which is 2.405. Put D equal to 8.5 and put the values of N1 and N2 that we are using. For example, 1.48 and 1.46, 1.48 for N1, 1.46 for N2. We can have the value of the critical wavelength. If we use a wavelength shorter than that critical wavelength, there would be another mode coming along that is not wanted in a single mode fiber. Actually, in a single mode fiber, attenuation is more of a problem, while in a multi-mode fiber, dispersion is much more of a problem. Reason being the fact that the modal dispersion is not present in the single mode fiber, while there are other types of dispersion in single mode fiber that we do face. And the most profound of it is the chromatic dispersion.